Welcome to Lecture 1.3. In this lecture, we'll be discussing chemical shift and how it can provide us information about the electronic environment of our hydrogen groups or our signals in 1H NMR. Now, that might not make too much sense right now, but hopefully by the end of this video it will. First, let's revisit this x-axis that I've been mentioning. Now, in units of ppm, which I won't go into too much detail about, but that's what the units are referred to as, we kind of have a left and a right side. Starting at 0 and ending at 14 typically for 1H NMR, 0 is labeled as upfield or shielded. Now, we call it upfield. This is where the shielded hydrogens will go, and we'll break that term down in a second. As you increase the ppm of a signal, and you move to the left, we call this signal or a move towards the downfield, right? This is where deshielded signals will go. They could have called it left field and right field, but that would have been too easy. And this is organic chemistry after all. So, what does it mean if a signal is found at a lower or shielded range or a higher deshielded range? What does that give us? Well, let's talk about shielding. Imagine for a moment two different hydrogens, one that's connected to a carbon and one that's connected to an oxygen. Now, very, very, very oversimplified, we can imagine the NMR machine as a machine that's trying to shoot radio frequencies at our hydrogen protons. However, hydrogens have a 1s electron orbital, and they have electrons that are present bumping around. Now, this is obviously not how many electrons hydrogen has, but, orbitals, they're flickering. What we can talk about is the idea that hydrogen, in this case, when it's connected to a carbon, has a lot of those electrons, right? Carbon isn't a very electronegative atom. We consider this a covalent bond. And these RF frequencies, while trying to reach that hydrogen proton, can be deflected by electrons. Some frequencies may wiggle through and actually hit, but some of these electrons are basically acting like a shield. Notice the wording. We would refer this hydrogen as shielded. To be shielded means that you have electrons around you. Now, put briefly, right? If you have, for example, a negative charge or a delta negative charge, that would indicate that there are more electrons in that area, a lot of electron density, and that would act as a shielding force, right? Or something that would shield your hydrogen. Remember that shielding moves your signals to a lower ppm, or they will appear at a lower ppm. But what about this example? Now we have oxygen. Now oxygen making a covalent bond to the hydrogen, but it's more polar, right? Oxygen is an electronegative atom. It's going to be pulling electron density from that hydrogen, giving it a delta negative charge and the hydrogen a delta positive, right? This is the idea of leads to hydrogen bonding. However, if we kind of redraw that orbital, we can imagine that these electrons are being pulled closer towards the hydrogen, or rather, closer towards the oxygen. Now, the NMR machine, shooting its RF frequencies, are much more likely to actually hit that nuclei and not be deflected. It's as if that oxygen pulled away the electron shield. And this is why we like to use this term deshielding or deshielded. The electrons you had around you have been taken or removed or pulled somewhere else. Now, that would again move us towards that deshielded area or increase the ppm. So with that in mind, right, there's going to be a correlation table, right? Correlation table that kind of shows you common ppms. It's quite complicated, and you can refer to it as you need to. But one thing I like to do is really focus on 4 core peaks. Okay, the 4 core peaks to quote-unquote know. Now, this isn't something to memorize, as we'll discuss very shortly. Memorizing chemical shift isn't the best strategy, as making assumptions related to chemical shift can lead you into problems. However, it's organic chemistry. We deal with a very small handful of atoms, right? Carbons, hydrogens, oxygens, maybe the odd nitrogen, God forbid a bromine. But at the end of the day, this leads to very common functional groups that we're going to see frequently. They're going to show up at pretty predictable ppms, and in my opinion, if you know these four, the rest don't require memorization and they can be referred to the table. However, these four are very common, and if you're always looking back to the correlation table, trying to figure out what the ppm of your signal is for every single signal, it's just going to waste a lot of time, which is precious during a test. The first signal, or range I'd like you to be aware of, is somewhere in the region of around 0 to 1.5. I'll be very approximate with these numbers. But in this low shielded region, remember this is where your shielded signals are going to be, this is where I like to put the quote-unquote boring alkanes. What I mean by boring is that they're typically not connected to anything that exciting, nothing that's pulling away their electrons and deshielding them. Right? Signals in this region are not going to be too exciting, although there are, of course, exceptions. But it's good to recognize that this lower 0 to 1.5 range isn't going to be too exciting. Now for something more exciting, a number I'd like you to keep in mind is approximately 2.4. This can range from 2.1 to 2.6, somewhere in that ballpark. But I've commonly seen this number, and it's one that I like to use for my problems. At this elevated ppm, it's very common to find hydrogens that are adjacent, that is one carbon away, from a carbonyl. This hydrogen is being inductively pulled. Its electrons are being pulled by that carbonyl, not super strongly. This isn't a very high ppm, but it's at an elevated amount. And there are many other ways to get a chemical shift of 2.4, but in my experience, very commonly, you should be thinking about carbonyls when you observe signals in that range. Now, another signal that's quite important is 3.5. At this point, I should keep in mind that this is not to scale. Now, 3.5, even more deshielded. How can I get even more deshielded? Well, this number is typical for being adjacent to an oxygen. Now, this is an sp3 oxygen. We're not sure what functional group it is. It could be an ester or an ether. But the question is, why is it at a higher ppm than the red signal at 2.4? Take a quick second to look at that and try to justify why that signal at 3.5 is at a higher ppm, or why it's more deshielded. The answer I have is that it's simply proximity. This oxygen is only 2 bonds away from that hydrogen, allowing it to pull even stronger, while you are 3 bonds away from the carbonyl oxygen in that previous case. Again, I don't expect you to, or rather, I would urge you to not memorize these numbers and apply them all the time, but to keep in mind that they're common numbers and things to think about when you see signals in that range. After all, it is organic chemistry. The last range I want you to be aware of is approximately 6 to 8 ppm, and this is where it is very typical to find benzene hydrogens, or hydrogens that are connected to an aromatic ring, like benzene. Now, they're quite elevated for a reason called anisotropy that I won't be really digging into in this course. But you'll see this on your correlation table, and it's a very useful range to remember. One good tip that I'll help you with is only consider benzene when your molecule's chemical structure or chemical formula has at least 4 degrees of unsaturation or more. Right? Remember that benzene has 3 degrees of unsaturation in its double bonds and 1 degree of unsaturation in its ring. So if you see signals in this range of 6 to 8 ppm, and your molecule has 4 or more DOU, it's not a guarantee, but it's pretty close to that you have a benzene in your structure. With that in mind, with these useful chemical shifts applied, let's take a look at one drawback of using chemical shift alone and by making guesses. Chemical shift is great when you know the structure you're looking at. Right? If I give you a structure, you can look at what's connected. We know exactly what's connected to what, and we can make our estimations around what the chemical shift should be. But be careful. It can be dangerous to use when the structure is unknown. What do I mean by that? Take a look at this molecule here. So, if I was to ask of the ppm of this signal, these 3 hydrogens located here, right, we might notice that we are one carbon away or adjacent to a carbonyl, which would put us somewhere in the ballpark of around 2.4. Great. What about these hydrogens here? Well, they are directly adjacent to an oxygen. That's 2 bonds away, they're closer, and we would expect them somewhere around 3.5. Now, remember I talked about those boring hydrogens in that low region. That's where we might expect to find these hydrogens. Now, this signal may be expected to find, we may expect to find around 1.5, and maybe this one around 0.9. Again, these are approximate numbers used for demonstration purposes. I'm not sure what the actual ones are for this chemical specifically. They're pretty close. One thing that's interesting to note is that this signal is more elevated, it's more deshielded than the one over here at 0.9. The reason for that is simply, once again, the proximity to the oxygen. You'll notice that these hydrogens at ppm 1.5 are simply closer to the oxygen. And that's why I gave a wide range for the boring alkane region. They can still be affected by electronegative atoms, but they're not directly connected to anything exciting. Where chemical shift can be misleading is when we look at these two hydrogens. Right? Here we see that they're not only beside a carbonyl, where we might expect a ppm of 2.4, not only are they beside an oxygen, right? They're also beside this oxygen, where we might expect them around 3.5. And we might actually observe this ppm somewhere around 5.6. Right? We're not going to add these numbers up, but keep in mind that both of these, this oxygen and this oxygen, both the carbonyl and the ether, are both able to pull electrons at the same time. That is, that the effect of these chemical shift changes are additive. Now remember, when we know the structure, with the structure being given, this isn't too unheard of. Right? Oh, of course, we can see that it's between a carbonyl and an oxygen. That makes sense. Right? The problem, though, is when we see an NMR spectrum and we see a signal at 5.6. If you don't know the structure, if you're trying to figure that out, right, and you see a signal at 5.6, you might be very tempted to look at your correlation table. And that correlation table might say, hey, that's pretty close to being a benzene. And if you make that assumption, you'll never get the correct answer, right? So be careful. Chemical shift is very informative, but if we make a big assumption based off of it, we might, mistake something like this. And no 1H NMR correlation table on a single page is going to have this specific example, right? You can find it online, but in a test, you're not going to find this specific example. It's not going to be on there. So keep in mind that while chemical shift is great, it's dangerous to use when we don't fully know the structure. Another example of this is demonstrated by this trichloromethane. Now, well, this wouldn't be the hardest NMR to do, but, let's talk about why this is misleading. A hydrogen that is connected to the same carbon as a chlorine on a typical correlation chart you might expect this to be somewhere around 2 to 2.4 ppm, right? Based on the correlation table that you have. So if this signal showed up at 7 ppm, you might be very confused, not sure where to go next. But given the fact that chemical shift is additive, that all 3 of these chlorines, these electronegative atoms, are pulling at the same time, it would make sense that this ppm is elevated. Once again, just keep in mind that it's a great piece of information that the signals give us, but it should not be used in its totality, and it's best to use when you think you know the structure and you're checking your work. Let's do one extra little deep dive into how resonance can affect chemical shift. Electron donating groups can be defined as a group connected to a benzene ring, or other systems, as we'll discuss in further topics in the course, that donates electrons by inductively using resonance like so. These are typical when there's a heteroatom with lone pairs directly connected to your ring. If this oxygen lone pair was to form a double bond here, we would move the electron density to position A. That would give us a resonance form that looks something like this. And we could continue that movement throughout the benzene ring. I won't draw the last form, but there's also going to be a negative charge on this carbon as well, just like it was on this. We'll definitely spend more time on the idea of electron donating groups and withdrawing groups in the topics to come. But let's talk about how this could affect resonance, or how resonance, rather, could affect chemical shift. Without considering resonance, we may expect signal A to be the most deshielded, as it's the closest to the electron withdrawing oxygen. However, keep in mind that the resonance form represents some percent character of the overall molecule, the true molecule being the hybrid. There is actually a delta negative charge, right? A partial negative charge because of that lone pair character on that carbon. Delta negative indicates the presence of electrons or shielding. And we may actually expect signal A to be more shielded than we would have otherwise expected. However, the most shielded signal would likely be signal C. That's because in this resonance form, it too gets the delta negative charge, and it's the furthest from the oxygen. That would leave B, then, to be the most deshielded signal, which is unexpected. Many students would put A due to its proximity. That's how resonance can affect the chemical shift. We'll look at one more type of group, the electron withdrawing group. These are typically depicted by a carbonyl being directly connected. Here we can see that a double bond could be pulled out, giving us resonance forms that look something like this. And while they look similar, you'll notice one key difference with the resonance forms, and that's that the benzene carbons are taking on positive character. Right, notice here that instead of donating electrons in, we're actually pulling the electrons out with resonance. So now these positive delta charges that are present on A and C, these are actually deshielding. We would now expect A to be the most deshielded signal, as it's the closest to the electron withdrawing carbonyl, and it's deshielded by resonance. However, unexpectedly, B would actually be the most shielded signal, as C, while it is farther from the carbonyl, right, which would make us think, oh, that's probably the lowest in ppm. However, it is deshielded by resonance. So keep in mind that that common mistake can be avoided by keeping in mind different resonance forms of your molecule. With that in mind, that's everything for chemical shift that I want to cover. In our next lecture, we'll cover integration and what kind of information we can get from that piece. I'll see you there.